Thanks.
Okay, can you see?
Yes, perfect.
Okay, so I can start. So in this talk, I will show you the progress towards a 4D tracking pixel detector, fast tracking pixel detector that is developed in the context of the TimeSpot project and also in the framework of the LHCb RTA project. So the TimeSpot experiment is an R&D project for a time and space real-time operating tracker. That is a 3 years project from 2018, founded by INFN in Italy, and it aims at the development of a silicon and diamond 3D tracker, including timing facilities. So it already demonstrated 30 picosecond hit resolution at a test beam at PSI. And so the final goal is the construction of a demonstrator that integrates sensor, electronics, and real-time processors. This is divided in different work packages, in particular, the development of 3D silicon sensors, diamond sensor, the design and test of pixel front-end, implementation of fast tracking devices, and the implementation of high-speed readout boards and integration of all the system. So slide 3, the 3D silicon sensors are a well-established technologies in which electrodes are realized as vertical columns instead of planar paths. And this has already been used for vertex detectors, for example, the Atlas IBL. So there are some pros and cons. The higher fabrication complexity and costs, for example, and also the geometric inefficiency. For example, the electrodes are blind. But this proved radiation hardness that is more than let's say 10 to the 16 neutron for square centimeters in the IBL in particular. And by design, they provide extremely fast signals because the charge position is decoupled from the electrode distance, and they prove real potential for timing that has not been exploited in actual experiment. So in the TimeSpot, the 3D silicon sensor are being developed with a trench geometry. That is what you can see in the first picture. And so these provide a best solution for electric field uniformity and a charge collection time that is less than 400 picoseconds. Also, there is a strong mitigation of lambda fluctuation, and the full depletion can be achieved at about 20 volts. So the first 3D trench batch was produced by FPGA in June of 2019 with different test structures, for example, pixel strips that are, let's say, 10 pixels connected to the same pad, and a single pixel and double pixel readout. Also, TimePix geometry, let's say TimePix compatible geometry was realized with 15 times 15 micron pixels. So the test beam was performed at PSI in the end of 2019. And in particular, only the test structures were tested with a 270 MeV pion beam. So the timing, that was the main focus of this test, is measured by the difference with two reference multi-channel plates that has 18 picosecond resolution, and the DUT time is obtained from custom fraction signal, custom fraction discriminator signal. So in particular, the timing contribution is the sum of different contribution, but we can see that without any correction, we already obtain a resolution of about 45 picoseconds, and with numerical filters to decouple the different contribution, the resolution is expected and measured to be lower than 30 picoseconds. So on the front-end ASICs development, the first front-end ASIC prototype on 28 nanometer CMOS technologies with a full pixel readout chain is being development. In particular, a mini ASIC has been produced. So it features a charge injection circuit, a charge sensitive amplifier with sensor leakage current compensation, leading edge discriminator, And in this version, it has only 8 independent channels and 3 TDC technologies to be tested for validation. So this has been tested. This was called, let's say, prototype 0. One test was produced and tested, particularly to gain confidence with 28 nanometers technologies. So the amplifier performance were about factor 2 worse than simulation. This was because an underestimated parasitic in the evaluation in the feedback loop. And in general, the overall measured time resolution was in the range of 150 picoseconds to 70 picoseconds, depending on the powering mode. So from low power and high power. Also, the test has been performed on the LVDS lines. So in a loopback configuration, there is a bit error ratio that is lower than 10 to the minus 15 in the low power mode. So in general, in the different power modes, the high speed links work in a, let's say, silicon proof way. So that's all for this task. Instead, about the tracking algorithm and tracking device, that is the main topic of this talk. We are developing this so-called 4D stub-based tracking. In particular, we use stubs that are defined as doublet of fits, and a stub provides a track hint with no assumption on the particle origin. And then, after the identification of doublets, geometrical cuts can be applied to filter the stubs that are not compatible with tracks from the luminous region. And also, the tracks are identified from cluster of stubs that have similar parameters. Moreover, if we include the timing, we can further suppress the combinatoric suppression using timing cuts. For example, the particle velocity is required to be compatible with the speed of light. So on slide 9, and there is a brief description of the parallel track finding algorithm. In the first stage, there is the identification of hit doublets that are so-called stubs that are geometrically and timing filtered. Then these stubs are projected to a 2D reference plane. So we have to know that the stubs have 5 parameters if we include the time, but the pattern recognition is performed only in a 2D reference plane in order to save resources. And so the tracks are identified as clusters of stubs with similar parameters. So these 3 points are basically reported to hardware in 3 independent modules that are the Stub Constructor, the switch that delivers the data from the identified stubs to the grid, and the engines that mimics the single points of the grid on the right. So the system has been implemented in FPGA with a highly parallelized architecture, also pipeline architecture for a low latency budget that is less than 1 microsecond. So in particular, FPGAs allows for reprogramming flexibility while keeping high performance in dedicated tasks. So we also put a particular focus to the latency. In particular, the data transfer between the modules is self-managed through the implementation of a custom hold logic that reduces the data serialization, and there is a guaranteed minimum latency. So slide 10, some brief results from the algorithm simulation. So we use as a case study the first 12 planes of the LHCb Velo detector. In particular, we simulated a pile-up condition of about 40 for a total of about 1,200 tracks per event. So the main results is that the track parameters are well reconstructed even before including timing, and the efficiency is about 99%. But the purity, that is 1 minus the fraction of ghosts, the purity is 64%. So what happens when we include the timing? In particular, we simulated a 30 picoseconds response of of the sensor, the efficiency stays high, but the purity increases. And also we can access the time, we can reconstruct, let's say, the time of the track. So the track parameters improves also when including the time information, the reconstruction is stable and the track purity improves. Slide 11, there is a brief report on the efficiency. So the reconstruction is, so the purity, as we said, increases from 60 to more than 80% when we included the timing, and also the efficiency is stable with respect to the track parameters that in this case are the radial and azimuthal value of the interception to the grid, the eta, the D0 and Z0. Slide 12, we illustrate the timing benefits. In particular, the track parameter resolution, as we said, improves when we include the time information. And also we can see that if the time resolution is, let's say, more than 150 picoseconds, basically it becomes useless. Instead, at 30 and let's say even less, the purity improves very well. So also the time can be used to reconstruct the time of the track. So the track misassociation, in this case, when we do not include the timing, is about 10%, when it is reduced to less than 1% when we use precise information. So slide 13, I illustrate the hardware architecture is still schematic, but in more detail. So as we said, this is divided in 3 blocks. So the stub constructor, in particular, one stub constructor is dedicated to the reconstruction of doublets in each couple of detector. So these modules are all independent and work in parallel. And then the identified stub values should be delivered to the engines through the switch. So the stub switches are also independent and process different area of the track parameters. And the engines cover the 2D tracking plane organized into multiple independent regions. So we have to note that there is absence of lateral communication between modules that makes the system modular and scalable. So the results presented here can be extended to larger design. Slide 14 is the detail of the stub constructor. So the stub constructor in the top left image process the hits from a couple of sensors. So sensors are divided into exclusive region, and only compatible region are processed by a dedicated stub makers. So sensor regions are optimized to have uniformly populated stub makers and reduce the total latency. And the hit data are delivered from the sensor to the stub makers through a dedicated hit switch for the, let's say, detector 1 and detector 2 in the couple. Instead, on the bottom right picture, there is a schematic of the stub makers that evaluates the combination of hits from 2 already compatible regions. It is composed by 2 independent buffers to store the hits, 2 multiplexer, and that performs a double loop over the buffer entries, and a filter to apply geometrical and timing cuts and suppress the fake combination. So in the simplest case, just one combinatorial unit is used, but we can extend to have a better parallelism with more resources, of course. So slide 15, a schematic of the switch. The switch is on the right image, is a full mesh network of sorters that are the basic units of these modules. So the data are delivered based on a pre-evaluated address that depends on the projection of the stub. And an old logic is implemented to pose the data flow when the data cannot be accepted by the following items in the distribution chain. So this is also to reduce the latency, but also to prevent the loss of data. So the engine mimics one cell in the grid where the pattern recognition is performed. So the stub coordinates are used to identify the cells, and a counter is in the let's say, identified cell is increased when the stub is received. So a track is identified if the central cell is a local maximum with respect to the lateral cells counter. And the candidate track parameters are evaluated as the average of the incoming stub parameters. Because as I already said, the stub already contains, let's say, a hint with all the track parameters. So slide 16, let's talk about the hardware implementation. So this system is being has been implemented on 2 boards. One is the Xilinx VC709 evaluation board that has a PCI Express interface, optical links, and 2 banks of DDR RAMs. And here we implemented the stub constructors. So on the right board instead, that is the GFX board developed by BNL at BNL for Atlas Calorimeter. It has 2 Xilinx Virtex UltraScale FPGAs, optical transceivers with up to 1.6 terabyte per second input data rate, and 1 Xilinx Zinc FPGA for control. So the switch and the engines and the fan-ins are fully implemented on this board. So we performed different tests, in particular for the stub maker test. We tested the combinatorial logic of the stub makers on the VC709 with no stub filtering at the moment, and using a reference clock of 200 megahertz and a buffer depth of 8. So data in excess are lost, but this is basically prevented by correctly distributing the stub makers in the system. So the test has been performed by sending different, let's say, events of n+1 hits, where the last is the end of event, and see if the combination are evaluated correctly. So during the processing of one event, a null logic is automatically generating and backpropagating, queuing the data, so preventing the data from another events going inside the logic. So the test passed, providing both the correct combination and proving also the old logic behavior in this model. And the implementation of the full stub constructor is ongoing. So the switch has already been tested because it is used in another part of the firmware, and the stub filter has to be finalized and tested. So about the stub makers, we also did a simulation, and we identified that the number of and the occupancy of the stub makers depends on how the sensors are divided. So we divided into all the system into all the sensor into 8 times 32 radial and azimuthal regions, and evaluated the number of correlated regions in the first and second sensor of each couple. So it turns out that we need about 15,000 stub makers for 8 detector couple in a Velo-like configuration. So this number does not linearly scale, but we can see that we need about 800 stub makers that produces the stubs that points to 1/64 of the full track parameter space, that is the space that we use for the second test, that is covered by the engines implemented in the GFX. So we also, in slide 19, evaluate the occupancy of the stub maker, also in a software simulation, and we estimated that about 50% of the stub makers is processing at least one data for each event. And in particular, for each event, every occupied stub maker has to process about 40 combinations. So in the pictures, on the left, we have the distribution of the number of active stub makers, and on the right, the distribution of the number of candidate stubs processed by the stub makers. That has an impact to the performance and timing performance. And with the shaded histogram, we have the number of filtered stubs. So the latency is dominated by the number of combination to process, even if more are filtered after. So slide 20, there is an estimation of the stub constructor throughput. So the goal is to process event at 40 megahertz rate. in the LHCb Velo upgrade 2 condition. And so we have to satisfy the equation on the left, where this depends on different values. So in particular, the frequency, the occupancy, that is, I consider the worst case, that is about 50%, and the number of identified pre-stubs for each stub maker, and the worst case is about 40. So with this number, the relation is actually not satisfied, and we obtain a processing rate of 10 megahertz, but there is a simple way to satisfy the relation, is to increase the number of combinatoric process within the stub makers by a factor 4, for example, using a stub maker approach like in the picture, so where the combination are processed in a more parallel way with more resources. And also the frequency could be in principle a bit increased, but this depends on the actual implementation. On slide 21, there is the we tested the switch logic plus the engine logic. So we divided all the space of track parameters into 8x8 sectors and provided to the system some already filtered stubs evaluated in software simulation. And we have to note that since the system is modular and scalable, thanks to the absence of lateral communication, the results from this sector are actually can be extended to the full system. So slide 22, there is the architecture of the test. So there are 3 blocks from the top to the bottom. So the data generator, where data from simulation are stored. All this system is implemented in hardware actually. And the device under test that comprises the switch plus engine plus the fan-ins to collect the results. And the data checker that contains the expected results from the simulation. So data are processed in the DUT, in the hardware, and the data checker compares that the received tracks data are actually the one expected from the software simulation. So we obtained that the data processed in hardware are actually compatible with the data stored in the output ROM. And also we obtain an event processing throughput of 40.9 megahertz. So the next step are the implementation of the full system. So with a software generation of simulated data on PC, then data will be transferred to the VC709 board with the PCI interface. Then the stub generation will be performed on the VC709, data transfer to the GFX, and the results collected to the first board and then to the PCI Express. The full system test is needed because at the moment all the modules have been tested singularly, so in independent boards. And there is a collaboration with INFM Bologna within the TimeSpot project for the development of our LHCb Velo Upgrade 2 simulation that includes timing information of the hits, and also for the development of clustering algorithm in FPGA. Also, we are going to improve the setup, upgrading the VC709 to Xilinx VC UltraScale 128 that has increased resources and transfer rate up to 1 terabit per second, so we can test the system with more data and more throughput. So just recap on timing. So why we are interested in timing, in using timing and real-time tracking, because timing in track reconstruction can help if it's very precise on the timing of the hit, so at about 30 picoseconds or lower, can help in the very first stage of the path recognition by use only compatible hits in the path recognition itself. And also, the timing is useful in the primary vertex association because it provides additional power to select the correct primary vertex and associated it to the tracks. So in this case, the conditions on the time are more relaxed, and 200 picoseconds are enough to separate tracks with similar spatial parameters. So also on slide 25, I just identified where an FPGA accelerator can be included in the LHCb, in particular where this system, that is the 4D tracking FPGA accelerator, can be included. So this system is studied to receive velo cluster and provide tracks in less than 1 microsecond. So could be in principle put in the trigger stage, and also the tracks could be provided together with a collection of feeds for a refined feed in the software stage. So as a conclusion, the TimeSpot developed a 3D silicon sensor with trench pixels that provided unprecedented timing performance with up to 30 picoseconds time resolution, tested at the PSI. Also is developing 28 nanometer CMOS front end with high precision TDC, and the electronics at the moment is the limiting factor for the full time resolution, and the optimization of the design is ongoing. Also, a stub-based fast-track finding device has been developed for a possible application to an upgrade to LHCb velo-like detector, and the system has been implemented and tested in FPGA. So the stub identification and construction has been tested in high level simulation. The main components of the Stub Constructor have been tested in hardware using a system clock of 200 MHz, and the assembly of the full Stub Constructor is ongoing. And the Switch Plus engine has been tested in low-level simulation and hardware that tested at 40 MHz event rate using a system clock of 320 MHz. That's all.
Many thanks, Marco. Questions to Marco? I had a question. In fact, I think you answered it in your last or one to last slide about the use of the timing. The timing is really used to distinguish the tracks from different pilot collision, right?
Sorry, I could not understand.
The timing information is used to distinguish the tracks from different pilot vertices.
Ah, here.
Yes.
So.
Yes.
Here you can see in the left plot what happens if you use the impact parameter, so on the x-axis, to distinguish the different primary vertex, and also the time. So if you don't use the time in this simulation, if I recall, there are 50 primary vertex. If you don't use the time, you have more primary vertex that are merging together. So these are the conditions of the upgrade 2. So it says that if you do not use the timing, it's difficult to use distinguish between different primary vertex. Instead, if you use a 2D approach, this will be easier in the future.
Okay. Okay, thank you. If there is no other question, I think we can move on. Thanks a lot, Marco.
Thank you.
Next.